Sorry. Okay, yeah. So let me first of all thank you for the opportunity to present our recent results from hadron spectroscopy at BES III during this workshop. And I want to start off my presentation here by shortly reminding you about the BES III experiment. We're part of the Beijing Electron-Positron Collider, which itself is a part of IHAB in Beijing. You can see a photograph of the complex here on the top right-hand side, and then a more schematic drawing here on the left. And so what we do is we accelerate electrons and positrons here, first in a linear pre-accelerator, then they're injected into two different rings, go in opposite direction, and are brought to collision here in the center of our experiment. And we do this in an energy range between 2 and roughly 5 GeV at luminosities of 10 to the 33 per square centimeter per second. That's at psi double prime peak. And so yeah, we looked into E plus E minus collisions roughly in the Charmonium region, and we do that in the center of our detector that's shown here on the bottom right-hand side from the schematic view. That's actually cylindrically symmetric around that beam pipe. And it's basically your prototypical hadron spectroscopy experiment, just as you would expect that to look like. We have a drift chamber here that allows us to measure the momentum of charged particles. We do have a time-of-flight device for particle identification, an electromagnetic calorimeter for photon detection, and then in addition, a muon counter here at the outside. And so with this detector, we have over the last close to 15 years now, accumulated many large data sets that are somewhat summarized in this plot that shows luminosities of these data sets as a function of the center of mass energy. And so let me start here on the left-hand side. We have, since the end of 2019, 10 billion J-psi on tape. We do have, since the beginning of this year, actually, 2.7 billion or close to 3 billion psi2s. That I think is also very important to mention, also gives us around 260 million Chi-C decays for each of the 3 different J's here. And with these data sets, what we can do is we can have a look at light hadron spectroscopy. We can also study eta and eta prime decays. And there'll be a dedicated talk on this later this week. From the psi2s, we can have a look into Charmonium transitions. We can study various different topics in hyperon physics and many more things. Then in addition, there's some data not shown on this plot, actually to the left of this plot in this energy range between 2 GeV and all the way up to the J-psi. That's roughly 700 inverse pico-1, which for spectroscopy purposes can, for example, be used to study excited rho, omega, and phi mesons. And then when it comes to the higher energies, we do have roughly 3 inverse femto-1 at the psi double prime peak. That is currently just right now as we speak being extended to, with the goal to go all the way up to 20 inverse femto-1 at the psi double prime. And then in addition, there's another large data set here of a little bit more than 3 inverse femto-1 right above the D sub S star D sub S threshold. And so these 2 data sets are our main data sets to do flavor physics, open charm physics, to look into D decays and D sub S decays. They also serve as our main sources for studies of ISR processes and for 2-photon physics. And then there's all these other data sets in this energy range, say roughly above 4 GeV or so, that we call the XYZ region. That's in total 22 inverse femto-1 that we can use for XYZ spectroscopy to search for new decays of XYZ states, but also to look into open charm production, to study charm baryons and many other interesting topics. So with this, let me start here with Charmonium and Charmonium-like spectroscopy. And I want to start this off by briefly repeating what the previous speaker already nicely introduced. And that's the Charmonium spectrum, where on the left-hand side here, you see the masses of Charmonium states as a function of their quantum number. And all the yellow boxes here are Charmonium states that have actually been observed. And all the gray boxes are potential model calculations following this Cornell potential, plus some spin-dependent terms that aren't shown here. And so behind all these yellow boxes, there's matching gray boxes. And so this has been regarded as extremely successful, and Charmonium has been regarded as to be fully understood up until the year 2003, when this new state was found by the Bell experiment, the X3872, in the invariant mass of the J-psi and 2 pions. And ever since then, several additional unexpected states have been observed that are shown here as the blue and then a single red box on the left plot. And so BES III has been one of the leading contributors to that field of exotic Charmonium-like spectroscopy. It's one of our main contributions being the discovery of the ZZ 3900, here showing us this peak in the invariant mass of a charged pion on a J psi. And so I want to start this topic of Charmonium and Charmonium-like states off with this column here with those states that share the quantum numbers with the photon, because those are the ones that we can actually directly produce in the collision in E plus E minus annihilation. And so the first thing that was found here was back at the time named the Y4260 and was found by Babar in initial state radiation. And then they looked into the invariant mass of two charged pions in the J psi and found this unexpected peak here. Now, what we can do is instead of use initial state radiation, we can directly set the accelerator to specific energy points in that region, and you gather high statistic samples. And we've done that, and what we find is that what was once seen at this one broader peak here by Babar is actually made up of by two peaks, one that's slightly lower in mass and slightly more narrow, and then this high mass shorter here. And so over the years, we've studied these resonances, what they're now called the Psi 4230 and the Psi 4360 in many different channels. And I've summarized all the BES III findings of these on the right-hand side here, where the mass and widths of states found in these different channels are shown. And what you can basically see is that there seem to be two clusters here. So we have one low mass state. It's not super clear if that's necessarily only one state, because we find very different widths between the different channels. And then there's a second cluster here at higher masses for this higher mass state. And so let me just maybe highlight one of these channels. That's one that was very recently published. It's an updated measurement of E plus E minus to pi plus pi minus and the Psi 2s. So what we're doing here is we reconstruct the Psi 2s in many different ways. On the one hand side, we look at Psi 2s to charge pions on the J psi. And then in addition, we also look into this channel where you have the Psi 2s decaying to the J psi in addition to some neutrals. And so this neutrals here includes the decay through an eta meson using a pion, using two pions, and also the subsequent decay of the Psi 2s to gamma chi C1, the chi C1 doing a radiative decay to the J psi. So that's all included in this neutrals channel. And so what we find here are these red data points in comparison to our earlier measurements shown in brown here. And it also compares really well with the earlier Babar and Bell measurements shown in blue and in green. And so the main feature of this cross-section is the heavier of the two resonances, the Psi 4360. But using this new precise data, what we also see is that there's on the level of slightly above 4 sigma, some indication here that the lighter of the two states is also contributing. And then on the higher mass end of this cross-section, what we find is that there's a peak here that was also seen by Bell and Babar before. And this corresponds to this Psi 4660. And this is actually the first observation of this state at BES III using newly found and newly gathered data above 4.6 GeV. And then another very interesting topic when it comes to these vector Charmonium-like states is open charm production. And so what's shown here on this slide is a very recent measurement of the process of E plus E minus to D star D and D star D star. And so what we do here is we reconstruct one of the two D stars that's shown here on the bottom left-hand side. So you reconstruct the D star, then look in the mass recoiling against that D star, and you find both the D and the D star. And so we can extract both of these two cross-sections in this single measurement. And what we find is consistent with earlier measurements by Bell, Babar, and Clio, just at improved precision. And so these cross-sections show very interesting structure. What you see here on the top right-hand side is E plus E minus to D star D star. That shows very significant structure just in this interesting mass region between, say, 4.2 and 4.4 GeV. And similarly, the D star D also shows some maybe smaller, but some very interesting structure here as well. we make no attempt at fitting this. We think it seems to be very complicated structures that will require more sophisticated models than just fitting a series of bright weakness to this. So we're looking forward to theory colleagues analyzing these channels. Good. So with this, let me switch topics here a bit and go towards what might actually be a conventional Charmonium state. A candidate to be the 1,3D2 Charmonium state, the Psi2 3823, that was originally discovered by Bell decaying to gamma Chi-C1. And so what we've done here is first look to establish a production mechanism for that state at BES III, and that's together with 2 pions. And so then you first look into this well-established decay channel gamma Chi-C1 that was previously measured by Bell. And we find that state here. And then having that production mechanism established, we can look for new decay modes of that particle. And what we find is evidence that it also radiatively decays to the Chi-C2 on the level of slightly above 3 sigma, but we find no evidence for any other new decay mode of that Psi2 3823, either due to pions on a J sign or eta J psi, pi 0 J psi, or gamma Chi-C0. What we do, however, find evidence for is that it doesn't matter if you have a pi plus pi minus pair here, or if you pi 0 pi 0. So in the case that you exchange charged pions for neutral pions, we still find that signal in the decay to gamma Chi-C1 with evidence on the level of 4 sigma. And this is actually consistent. So production is consistent between the charged pion and neutral pion channel with isospin symmetry. And then there's a new measurement on this that appeared on the archive just yesterday. And so what's done here is that you look into exactly the same channel, 2 charged pions and a Psi2, with the Psi2 decaying to gamma Chi-C1. And the big difference here is that we allow for one of the photons to be missing. So we identify the Psi2 and the recoil mass of the 2 charged pions, and then allow one photon to be missing here. This increases the reconstruction efficiency quite a bit and allows us to measure the cross-section of this process, which is shown on the right-hand side here, and clearly indicates that there's some resonant contribution to this cross-section, at least here in this mass region of, say 4.4 GeV or so. And then there's a hint that there might be a second resonant contribution here at higher center of mass energies, but that's not very significant. What we also tried to do is look into the angular distribution of the Psi2 production. So this is the angular distribution of the Psi2 in the center of mass frame. And the idea here is that at the tiny phase space that we have, it's very likely that that pion pair here is in a relative S wave. So let's say this comes from a sigma. And then if the state that we're producing is actually a Psi2, then that has to happen in D wave. So with L equal to between the pion pair and the Psi2. Whereas if what we're producing here is a vector state, that can also happen in S wave. And so we can compare the experimentally measured angular distribution with the hypothesis of L equal 2 and L equal 2 transition, as well as an S wave transition. And while the data seems to slightly favor the L equal 2 assignment, that's right now roughly at the level of 2 sigma, so not very significant. What's also done in this new paper is mass and width measurement of the Psi2, actually finding the most precise value of the Psi2 mass yet, at the best upper limit when it comes to the width of that state at smaller than 2.9 MeV. Good. With this, let me come to the last topic I have here for the Charmonium and Charmonium-like spectroscopy. And this is the discovery of the ZZS that was made by the end of last year. There'll be a dedicated talk on charged Charmonium-like states by Yuping later this week, so I won't go into much detail here. So let me maybe just summarize what we did. So what we looked for is the plus and minus annihilation into a charged kaon, and then either a D sub S D star or D sub S star D. The reason we look into both of these processes at the same time is that we're using a partial reconstruction method here. So we aim to reconstruct the K plus and the D sub S minus, and then look into the recoil mass of that system. And if you do that, you see that you find a peak here at the D star mass. However, the second process here, we have an excited D sub S instead of a D star. also gives you a slightly broader peak, but at the same mass position. And so we can't disentangle these two processes. This is using new data sets above 4.6 GeV that we were not in our energy reach before. And so what we find is summarized here on the right-hand side. That's the recall mass of the kaon. And you see that at this one center of mass energy of 4.68 GeV, you find an excess close to threshold, close to the D sub S D star or D sub S star D threshold, and on the level of slightly above 5 sigma. And so now if you interpret this excess as a particle, then this means that it couples to at least one of these two channels that we can disentangle, the D sub S D star or the D sub S star D, which would suggest that if interpreted as a particle, this would have to have a minimal Bohr content of CC bar SU bar, which would be a new category of these Charmonium-like states that has open strangeness. One should also mention here that shortly after we made this discovery, also LHCb reported evidence, or actually an observation of a ZZS state at 4 GeV. So the masses of these two are very consistent, but the width of the state that was found by LHCb is a lot wider, and so it still remains to be explored whether or not these are actually the same states or something different. And so it's, I think, very important that we keep looking into J-psi and 2 kaons, and that LHCb or the B factories look into these BDKs into D sub S D star or D sub S star D, just to be able to confirm what the other correlations are. Good. So with this, let me switch over to light hadron spectroscopy. And I want to start here with a topic where it's, I think, very nice to show how this evolved over time. So this is the radiative decay of the J-psi into an eta prime and 2 pions. And what you see here on the left-hand side is the invariant mass of the pion-pion eta system based off 58 million J-psi. And that was the discovery of this X1835 state. And then 6 years later, if you repeat the same measurement at roughly 4 times the statistics, what you find is that there's an additional peak here on the left, and then there's maybe two more peaks here at higher invariant masses. And if you already know what you're looking for, you might also actually wonder what exactly is going on here at the proton antiproton threshold. And so again, 5 years later, based off 1.3 billion J-psi, you get the plot that's shown here on the right-hand side, where you see the X1835 having this irregular line shape with the sudden drop-off at the proton antiproton threshold. You have in addition, these two structures called X2120 and X2370, and you might even wonder if there's maybe a fourth state hidden here on the right. Now we have very recently published the same channel using the full 10 billion J-psi that we have today. And then what you see is, again, you can very beautifully see this irregular line shape of the X1835 at the proton antiproton threshold. And you do actually see 3 more structures here on the right-hand side, the 2120, the 2370, and the new state that we now call the X2600. And so let's have a more detailed look into this X2600. And what's very interesting is the 2 plots that are shown here on the right-hand side. These are for 2 different eta prime decays, but in principle showing the same thing. That's the pion-pion mass distribution as a function of the eta prime pi mass distribution. And to be able to actually see structure here in detail, what's been done is that the F0980 region here has been cut out and the eta C has been cut out. And then what you see in structure here is that this new hump at 2.6 GeV that we find seems to be correlated somehow to pion-pion invariant masses around 1.5 GeV. And so if you look into this and again a little bit more detail and actually have a look into the pion-pion and the eta prime pi mass distributions, you find this very nice peak at 2.6 GeV, roughly 2.6 GeV. And at the same time, if you look in the pion-pion mass distribution, you find that there's a peak very close to 1.5 GeV, but also some more complicated interference pattern. And so what might be happening here is that you have a contribution from the F0 1500 as well as a contribution from the F2 prime 1525. And that there might be significant interference between the two. And it's at this stage not very clear how to interpret this very complicated pattern. And so more studies on this will have to be done. Generally, also more studies on the X2600 that also include a determination of its JPC quantum numbers. Yeah, we've also looked into the same channel using electromagnetic Dalitz decays of the J psi. So you place the photon in the radiative decay by an electron-positron pair. And we can do that and actually find basically the same structure that we also find in the radiative decay, albeit at much less statistics. So you do see the X1835, you find the X2120, the X2370, and might even see an indication here of the X2600. And so what you can then also do in these electromagnetic Dalitz decays is determine the transition form factor for this decay of the J psi to the X1835. And that's what's shown here on the right-hand side, parameterized by this pole term. And what we hope is that this will be a useful input for theory when it comes to identifying what the nature of that X1835 actually is. Yeah, then another topic I want to discuss here in light hadron spectroscopy are the light scalar mesons. And I'm sure most of you are aware why that's a particularly interesting topic. That's because the lightest glue ball is predicted to be a scalar particle. That's the one marked here on the left-hand side. That's predicted by lattice QCD to be slightly below 2 GeV. And the very intriguing thing about this is that there's 5 well-established isoscalar scalar mesons, the sigma of the F0980, 1370, 1500, and 1710. But there's only 2 isovectors, the A0980 and the A01450. And so that is seemingly an overpopulation, which together with this lattice QCD prediction is a very intriguing situation. Now there has been recent partial wave analysis of the eta-C decay into an eta and 2 pions by Babar. And what they found very interestingly is an additional A0 here at slightly above 1.7 GeV. And so that changes this whole overpopulation situation maybe a little bit. And so it's very, very important that this observation by Babar is looked into. And one of the ways we can do that is using D sub S decays. So what we do here in these, to study these D sub S decays is to use the double tag technique, which means that we produce a D sub S star pair that, for example, is the center of mass energy right above the D sub S star threshold. And so you tag one of the D sub S's in some well-known, well-studied decay channel. And then look for the D sub S decay, signal decay that you're interested in on the other side here. And so for these 2 studies, I'm going to be presenting on the next slide the channels that we're interested in are K pi with either charged kaon pair or neutral kaon pair. And so this is how that looks like. In both of the 2 cases, the partial wave analysis has been done to identify resonant contributions here in the kaon channels. And what you see on the left column is for charged kaon pair, and the right column here is for the neutral kaon pair. And by eye, these look very different. The main reason for that is that you have the huge phi contribution in the charged kaon channel that you can't have in the neutral kaon channel. But even then, if you look closer into this, you find a very, very interesting difference. And the difference is that in the charged kaon channel, you find a strong contribution close to 1 GeV, which is dubbed S0980 here. That's just because we can, in a single channel, not disentangle between isospin 1 and isospin 0 components. And you find only a small contribution in the 1710 region. Now on the K short, that's completely different. So you find a vanishing contribution in the region close to a GeV, but a very large contribution in the 1710 region. Now, how does that make sense if you believe in isospin symmetry? Well, it actually makes a lot of sense, because if you construct isospin eigenstates for isospin 1 and isospin 0 from these kaon pairs, what you find is that in isospin 1 and in isospin 0, the charged kaon states have the same sign, whereas the neutral kaon states actually have a different sign. And so you can explain this feature that you have strong S0980 contribution in K plus K minus just by a constructive interference between an A0 and an F0 in the 980 region. And that interference pattern would be completely opposite in the K short channel, so that you there would have destructive interference and this vanishing S0980 contribution. Now, to be able to also explain what happens in the 1710 region, where that signal is small in K plus K minus, but large in K short, you can also explain that by the same interference pattern, but that would mean that we need an A0 1710 to be able to explain what happens here in those channels. So these two analyses point towards an indirect observation of this A0 1710 state. And we're eagerly awaiting additional studies here, for example, on the D sub S decay, where you have a K short and the charge K on, where then this should directly be visible where there's no F0 1710 contribution allowed. And that'll hopefully be available soon. And then last but not least, I want to end my talk by this recent observation of a new spin exotic particle. Again, there'll be a dedicated talk on this given by Wei Zhang on next Monday, so I won't go into much detail here. So what's done there is we looked into a partial wave analysis of the radiative decay of the J psi to an eta and an eta prime. This is one of these radiative J psi decays that's supposed to be particularly gluon rich and thus favorable to produce gluonic hadrons. And so what we find here, among many other interesting features that I'm sure Wei Zhang will talk about in much more detail, is a new isoscalar spin exotic resonance eta 1 1855, just the mass that the name would suggest, with a width that's close to 200 MeV or so. And so that's this this purple peak here that you see in the invariant mass of the eta prime system. And if that doesn't convince you, then let me point towards the angular distribution here, where the black points show the data. The red line is the fit result that you get if you include this eta 1 contribution, and the blue line is the fit result that you get for this angular distribution if you don't include the eta 1 contribution. And while this alone maybe is not super convincing yet, if we change the mass range before we plot this angular distribution to the mass range where you actually find the eta 1, then this is what you get. And again, the red line here is the angular distribution that you get including the eta 1 contribution, and the blue line is the best fit you can obtain if you don't include it. And I think this is very convincing that this spin exotic part is needed in this partial wave analysis. And so right now, what we now have to do is to look into other production channels or other decay channels of this particle to gather more information, to not just be able to say this is a spin exotic, but to also have a chance of understanding what the nature of this new spin exotic particle actually is. So with this, let me come to summary. We've been taking data since 2008 now, and have in general a very broad physics reach, of which I only presented the spectroscopy part, but there's many other interesting topics in flavor physics, open charm physics, and precision measurements of R, of transition form factors, and many other interesting things. We have several new data sets that are currently being analyzed. I've shown first results both from the new J psi data as well as from new XYZ data, and there's many more interesting results to come in the immediate future. We're still taking data. So we've just recently finished upgrading our psi2s data to close to 3 billion psi2s. And I'm right now taking data to upgrade our psi double prime data set to 20 inverse femto1. And that'll not be the end for BES III. So we do have new data in new energy range we weren't able to cover before. 4.7 GeV all the way up to very close to 5 GeV that is available and currently being analyzed. And then in further upgrade in energy has actually already been approved. And will be done by the end of 2024, most likely. So that will extend our energy range up to 5.6 GeV, and will also allow us, like for these higher center of mass energies, to roughly triple our instantaneous luminosities. With this, let me thank you for your attention, and I'm looking forward to questions.
Thank you, Nils. Yeah, we're open for questions. So, Eulogio.
Yeah, thank you very much. You see, I was very happy to see, this work about the A01710. Very nice. You see, but I don't think there is overpopulation of states, because of scalars, because all these, the sigma F0500, F0980, the A0980, and all this, they were from long ago, they were reproduced, from the pseudoscalar interaction in the chiral unitary approach. And later on, Li Shengeng, one of your friends, he did, a work in which he also found other works, other of these resonances from the vector-vector interaction. And one of them was the F07010. Okay, but not only, he also predicted that, with the same interaction that there was an isospin 1, state, what you call now the A01710, about the same energy. And I was also pleased to see, there is a recent paper by Fenkungu, Meisner and collaborators, in which, in the region of applicability of the model, they also get, the state. So, two independent groups, they get the A01710, the F01710, but also the A01710. So, that's very nice. And because, we trust, our theories. I did recently a paper with Li Shengeng and Lian Rondai, and in which we show the consistency of this picture, this molecular picture for that state, with the data that you have presented in those of Babar. This paper is published in European Physical Journal C. You will see that in the web. Very nice. I think that was a very nice finding. Thanks very much.
Thank you. So Christoph.
Hi, Nils. Thank you very much for this very nice talk. Could you go to page 8, please?
8, yeah, sure.
I think it was 8.
This one?
Yep, this one. Actually, on the lower left, the picture, you said it shows 2 peaks. For my eyes, it doesn't. It shows 1 peak with a shoulder. And I think to understand how many states there are in that data set, what would be very interesting to see if one can get this filled with more additional data points. Is there anything planned in the foreseeable future?
Yeah, so this measurement dates back to 2017. Let me go one slide further. So you see already here, if you compare the brown data points with the red data points, that we do have additional data to fill in gaps here. And so the pi psi measurement is currently in internal review, and that should appear shortly.
Can you give me a timeline for what shortly means?
Yeah, it's pretty difficult to say. So at least by the end of this year, but I would hope that this would go faster.
Very nice. I'm very curious. Thank you very much.
Changsheng, can I make a very short question? Changsheng?
Okay, please.
Yes, concerning the same issue of the A11710, I saw by reading your paper, that you promised that you are doing a reaction which is the DS going to pi 0, K plus, K0 short. In which you see the A01710 without interference with the F0. How is this reaction going?
Yeah, it's also an internal review, and I think I'm not supposed to talk about that too much. But yeah, I probably wouldn't have included this very prominently in the talk if it didn't look promising. Let me just put it like this, maybe.
Yeah, can you tell us, when we will see the light, when this will see the light? When it will be made public?
I think it's pretty advanced in internal review, so it should appear on a shorter time frame than what I just said to Christoph for the pi side.
Okay, very good. I'm really looking forward. Thanks very much.
Thank you. So are there any more questions or comments? Nils, I have one question. Will you move to slide 12? On this X3823. Yeah, if you look at the plot on the right hand, it seems there are only a few energy points between 4.45 to 4.6 PV. So is there any plan to add more data in this energy region?
That's a really good question that I can't really answer right now. So what I know is that the data taking plan currently foresees to accumulate these 20 inverse femtobond on the psi double prime. And I'm not aware that there's any fixed data taking plan beyond that for now. But I think it would make a lot of sense to fill up that energy range. I just can't make any promises at this point.
Another question related to this analysis is it possible to measure inclusive pi recoil with psi 2 3823?
Yeah, that's a good question. I mean, it's certainly possible to look for that. I'm not sure what the signal to noise ratio is if you have a chance to see such a tiny signal. I'm aware that this has been tried for the I think X3872.
Yeah, I guess it's not so easy.
Right. Yeah. So I think it's not so easy, right?
Mm-hmm. Yeah, I have another question on the slide 18 on this X2600 to pi eta.
Mm-hmm.
Yeah, you mentioned. Yeah, maybe next slide. Yeah, you mentioned there are interference between F0 1500 and F2 prime 1525. But we know this F2 prime decay to pi has a very small branching fraction. If there's a real F2 prime to pi signal here, that means that we can see a huge signal in KK eta final state.
Yeah, I think you're right. So the KK branching fraction of the F2 prime is the dominating one. And that's certainly a channel that we're interested in and that we're looking for. That's also somehow connected to the last bullet point that I made here, that it's important to also look into the JPC quantum numbers. Because doing a full partial wave analysis of this channel with the pions that's shown here is extremely challenging and extremely complicated. But if you look into the channel wave for K short pair here, that changes significantly. And one of the points is that you can't have background with a pi 0 instead of a photon here if you have 2 K shorts, because that background would then be C parity violating. And so that's a channel that's actively being looked at right now. But I can't talk about that much more beyond the fact that we're looking into this.
Okay, so thank you. So are there any more questions or comments? It's no. So yeah, thank you, Nils. So I think this is the end of this session.